Hello friends. After understanding all the different parameters which affect bearing performance, now it's time to understand real life design problems. So they are basically categorized into two types, and so we will study the different design problem. So design problem 1 is the condition in which the load on the bearing is already known. So maybe there may be so many real life applications wherein we know that the load on this bearing is maybe 150 kgs. That means this is the load that the bearing has to carry, and then we have to check that under that acting load whether the bearing having certain values of L by D ratio, psi and viscosity will perform satisfactorily. Now to understand this, we have to see what is the process of bearing design. For hydrodynamic bearing design, one has to have a good engineering sense, and based on that he has to select certain values of L by D, certain values of psi and certain values of lubricant viscosity. This is very crucial, and that is why we have discussed at length the importance of these different parameters. So based on that, one has to have first trial versions of L by D, what is the relative diametral clearance, what is the bearing clearance, and what is the value of viscosity of the lubricant that he has to choose. Once he has these values in hand, and also the load comes from the client. So the client says that suppose I want you to design a bearing for so and so load, then the design engineer will have to see if the bearing performs satisfactorily. One may ask, what is satisfactory performance? So the satisfactory performance can be very easily understood as that the bearing should work under complete liquid lubrication conditions. What that means is, it means that there should be no contact between the journal and the sleeve. If this is achieved, then we can say that the bearing is performing satisfactorily. Now let us see what are the conditions in which the bearing is working satisfactorily. So for that we have to understand what is the film thickness the bearing is actually operating at. If the film thickness is above the critical film thickness, which we discussed earlier, if the H minimum that is obtained by calculation is above the critical film thickness, then we can conclude that the bearing actually is running in a very satisfactory condition, that there is complete separation between two surfaces and the bearing life will be good. So therefore in this problem one has to understand what is H min. So before we go into the procedure, let us see how we can understand this formula. H min is equal to C into 1 minus epsilon. So the following formula helps us understand how to calculate H min. So let us see this illustration. Here we have a bearing in operational condition. That means it is operating and there is a certain minimum film thickness and the bearing is basically in the continuous running condition, and the journal is running in the anti-clockwise direction. Now there are certain points to be mentioned here. So this gap between the journal and the sleeve where it is minimum, that is basically the minimum film thickness, and this is what we want to check. If this minimum film thickness is greater than the critical film thickness HCR, then we are safe. However, if it is not, then we have to go ahead and do another iteration of design. So now we will just see what this H min is. So this H min has to be calculated in terms of eccentricity E and the clearance C. So in this condition we will see what are these 2 points. This point is the center of the journal and this point represents the center of the sleeve. And what is E? E is the eccentricity, that is the distance between the center of the sleeve and the center of the journal. Now if you see very carefully, the eccentricity ratio, or so eccentricity ratio changes between 0 and 1. Similarly, the eccentricity also varies. The eccentricity can be 0, and when the eccentricity is 0, then the bearing looks like two concentric circles. So that is one extreme. And the second case is eccentricity can be equal to clearance, and in that case we can see that the journal is resting on the sleeve. So this is the second case, and this is the operational condition where eccentricity lies between 0 and C. So from the very simple diagram, if we connect these three dots, we can say that H min is equal to clearance, which is the difference between the diameters divided by 2, minus the eccentricity of the bearing. So therefore, if the eccentricity is completely 0, then that is the condition in which there is concentric bearing, and if eccentricity equal to C, that means there is touching. So if it has to be in between, so therefore that H min will automatically be equal to C minus E. So if this is understood, then we can very easily simplify this. This H min becomes equal to C minus epsilon times C, because eccentricity is epsilon times C. So then we can further simplify it, and therefore this becomes C into 1 minus epsilon, and that is nothing but the formula that we have seen here. H min is equal to C into 1 minus epsilon. So if it is understood how we calculate H min, then we have to go ahead with the actual design procedure. So the actual design procedure entails that first of all one calculate the load coefficient. In this formula we know what is P, because that is the requirement of the customer, and all of these other parameters we are assuming based on the experience. So then the only thing that is unknown is your CL. So one goes ahead and puts in all the values and finds out what is the value of CL. The back value of CL is known, and also the L by D ratio is known. So based on this one can determine what is the eccentricity ratio. So for example, if I am getting a value of your CL something like 1.4846 or somewhere in between this, and the L by D ratio is something like 0.75, then I can back calculate and interpolate and get what is the value of epsilon. Once this value of epsilon is known, then the next thing that we have to do is plug this value of epsilon in this expression and get the value of H min. Okay, so once this H minimum is obtained, there are only two possibilities, and the two possibilities are this. One is H min can be greater than HCR, then the bearing operates under liquid friction and the design can be accepted. And however, if H min is less than HCR, then we have to again take an iteration of design. Now what can be done? There are two possibilities. You choose a better material, that means you reduce the HCR by improving the surface finish of the bearing and the journal surfaces. That is one option. The second option is you can increase H min by increasing the clearance. So you can have a larger clearance and therefore H min automatically goes up, or by increasing the L by D ratio. So if the L by D ratio increases, then also you can get the desired result. So that is the process for design problem 1. There can be another design problem, and in this design problem, based on the materials that are being selected, the minimum film thickness value will already be known. So for example, if operating condition is known, for example, the dirt particles should be passed and there should be no scoring, so this is the value of H minimum. Or if you have finely bored bronze bearing, then this should be the value of H minimum. So if the value of H minimum is known and you are assuming certain values of L by D, psi and mu, then we have to check what is the capacity that your bearing can take. Okay, So this is the second design problem, and this design problem is relatively very simple. So if h min is known, then from the formula here, the value of eccentricity can be calculated. And if the value of eccentricity is known, then from the given value of eccentricity and L by D ratio, one can determine what is the CL. And if the CL is determined, maybe something like 2.51 based on the values, then that CL can be plugged inside this expression right here, and the load capacity of the bearing can be calculated. Once the load capacity of the bearing is understood from design problem 2, there can be again two possibilities, that the load can be very easily taken by the bearing, or it cannot be taken. So there can be different methods. If you want to go ahead and increase the load capacity, again one can change the kind of oil that is being used. You can use a very thick oil and increase the viscosity of the oil and the load carrying capacity, or one can also increase the L by D ratio and improve the load carrying capacity of the bearings. And in this way the iterations can go on, and one can achieve the optimal design and go ahead with the actual manufacturing. So these were the two design problems the engineer has to face in real life. Thank you.